This is STA 381, Chapter 6, Section 1, Numerical Summaries of Data. All right, so we're heading into Chapter 6 now, and we're going to start looking at, let's say you have a set of data and you want to make some sense of it. So the way we usually start with that is through looking at numerical summaries and graphical summaries of data, just getting an idea of what's going on with our data. And so just think anytime you have a data set, that's really where you want to start after you know that the data set has been cleaned up and is ready to use, is you want to do some summaries and to find out basically some ideas of center and spread, the shape of the data, are there any outliers present. So we'll be coming back to that theme over and over again throughout the rest of the semester basically. Okay, so numerical summaries of data. So we're looking at some sort of data, maybe we're just starting with one variable, say you're looking at height for people, and you want to summarize that set of data. And so first of all, we have a couple of different terms floating around that we've been talking about throughout the course. One is the population, and that is the entire set of data that you're interested in. Now that may not be what you have in front of you. In fact, it probably isn't. Let's say you're looking at the height of all males in the United States. All males in the United States is my population. And then a portion of that population, if we draw it probabilistically, is a random sample. So we didn't just ask the first 10 people that we saw, we found a way of drawing that set of data in a random manner. And so we're going to gain some sort of idea about what's going on with our set of data based on our random sample by looking at some summaries. And so just keep in mind that we're going to be looking at describing our data in terms of the shape, outliers, center, and spread, or SOCs. So just keep in mind shape, outliers, center, and spread. There are many different ways to talk about those aspects. And so we're going to present some here, but it is by no means anywhere near an exhaustive list. So let's start with a measure of center, which is our sample mean. Now this is the most commonly used measure of center. It's the one that you know how to use. You've been using it for years and years. You find the average of your test scores, or you find the average length of a sample of components. So you are very familiar with the sample mean. So we're quantifying this a little bit more formally. So if you look formally at the notation here, we see that we have n observations, we denote them by x1 up to xn. Then the sample mean is just found by summing up all those observations, dividing by the number of observations that you have. And if we're looking at, say, a population, because that's the sample mean, x bar, if we're looking at the population, then that actually changes a little bit. Terminology changes a little bit with sample mean versus population mean. So first of all, x bar is our sample mean. And as you've seen, mu is our population mean. And that is not just restricted to probability distributions. If we're talking about an entire population, we talk about mu being the population mean. And so mu is going to be summarized in the same way if we're looking at not weighting it with respect to some probabilistic distribution, but if we want to look at it and first talk about that way of looking at a sample mean, if we're looking at the sum from I equals 1 to capital N, so because capital N will signify the number of items in our population, then we have the sum of our all of our x sub i's. Now if we are looking at in terms of a probabilistic distribution, so just remember we have the weight here is our f of x sub I, but if everything has an equal weight, then it'll be x sub I divided by capital N. And so that's our sample mean and our population mean. All right, so let's look at an example just to get a quick idea just how to look at this notationally. As I said, I know everybody's very familiar with it, but just look at the notation here. So we see a set of data of pull force from engine connectors as shown in the table, and we see that we have I equals 1 to 8. We have our X sub i's, and those are just the pull forces from 12.6 down to 13.1. The sum is down there at the bottom, and then the average, according to Excel, is found in the manner that you see there. The reason why I really want to highlight this particular slide in this example is because of what you see there near the bottom. So notice near the bottom of the slide, you'll see a dot plot, and on that dot plot you see all of the data points, and then you see a fulcrum in the middle of the dot plot. That's your sample mean, so it's the balance point. So think about your sample mean as either a balance point or that place where you put the fulcrum, which would provide, just like you have a teeter-totter and you try to get people on there so you kind of balance in the middle. It's the same idea here. That is what your sample mean represents. So that's one measure of center. As I said, there's lots of measures of center out there. There's the median, there's the trimmed mean, there's all sorts of other measures that you could be looking at. So just because we've only talked about one doesn't mean that's the only one. So I do want to mention the median as well, just really quickly. And the median is just simply your middle observation. If you were to order all of your values from lowest to highest and find the middle observation where there's an equal number to either side, then that would be your median. And if your median happens to be of an even set of numbers, then it's the average of the two middle. So I just wanted to mention that really quickly. It'll become apparent in a few slides or a few lectures that we'll be talking about that from time to time. Variance. This is a measure of spread. So let's talk about that. So if we have n measures or n observations from a random sample, so x1 up to xn, then the sample variance s squared is basically it is the typical or average deviation that an observation is from the mean. So take a look at that for a second. So we have x sub I minus x bar. This is a deviation from the mean. We square it. Why do we square it? Well, we square it because if we were to, and then we add them up, if we were just to add up just the deviations from the mean, they would sum to 0. So what we had to do is we had to square those and then divide, because it's an average deviation, we divide by n minus 1. And we'll talk about why we do that in a few minutes. So you might be thinking, how is this an average deviation? Well, when we talk about the standard deviation is equal to the square root of the variance. And that's actually your average or typical distance that an observation is from the mean. We actually like to talk about standard deviation more than variance because variance is in squared units. Standard deviation is in the units of the original variable. Oh, before I go to the next slide, I want to talk a little bit about, at the very bottom of the slide, it says, for capital N observations in a population, the population variance is going to be analogous, again, to the sample variance. So the population variance, I'm going to write this down here, again, is signified by sigma squared. So you've seen sigma squared before at this point. And if you want to think about it probabilistically again, like we did with the sample mean or the population mean, I equals 1 to capital N of x sub I minus mu squared times f of x sub I. And so what we have here is a weighting here by each, what the weight is for each value, so what each probability weight is. But again, we're in terms of equal weighting, so it's going to be the sum of I equals 1 to n of x sub I minus mu squared divided by capital N. All right, and so that's analogous too. So you might be noticing, why do we divide here by n, up here by n minus 1, and we'll talk about that in a minute. So standard deviation, as I said, it is the square root of the variance. Sigma is going to be the population standard deviation. S is going to be the sample standard deviation. And as I said, and I'll write this down for you because this is an important way to think about standard deviation. So standard deviation, and this is just a heuristic definition, is the typical or average distance an observation is from the mean. Okay, so let's look at this example so you can kind of see how it plays out. So we see we have a set of data here. X is in pounds. We have the mean is in pounds, variance is in pounds squared, standard deviation is in pounds. So if you take a look at the set of data, the x sub i's, that's that same data that we saw from before, and we see our x bar is 13. So then the next column actually has x sub I minus x bar, and so you can see there that you have just x sub I minus x bar. And so you see there's a sign attached to those. Some of those are negative, some of those are positive. Notice that the sum is 0. Again, that's why we can't just look at the average deviation without squaring it. Then if we take the square of each one of those, we add them up, divide by n minus 1, so divide by 7, and you see that we end up with a variance of 0.2286. Take the square root, and we end up with a standard deviation. So that standard deviation is the typical distance that one of those observations is from the mean. And so that's how you would have to do it if you were wanting to do this by hand. Now, I'm going to tell you, the only reason I put this up is so you could see the breakdown of how standard deviation and variance actually works. You won't be doing this by hand. You will be using some sort of software, whether it be R or Excel or something like that, to actually calculate your variance, your standard deviation. And you can also do it in your calculator. One more time to take a look at this example. The only difference is that instead of using this definition form that you see right here, you can actually just do some algebraic manipulation to make it a little bit easier to work with if you wanted to actually do it by hand. And so this is just what we call a computational form of the standard deviation and the variance. So notice that it's the same set of data. We just input, now we're looking at the sum of the x sub I squareds, and then notice that the second term is the sum of the x sub I quantity squared. So what that means is that you sum first and then you square, and you notice they end up with the same answer. So if there's ever a case where you actually want to use that, I would go for using the computational form rather than the definitional form. Okay, so what's with that n minus 1? So the population variance that we have down here is calculated with capital N, which is the population size. And so the question is, why are we not dividing up here by n minus 1? Well, the true variance is based on subtracting off mu, which is our true population mean. There's no estimation that goes on with population values. They are the entire population, so there's no estimation. But the sample calculation up here uses x bar, and that x bar is an estimate of mu. But as we already know, x bar and mu are not going to be the same. They're different values because this is just taken up of a sample of 10, sample of 100. And so that n minus 1 is compensating for the error to help provide a more unbiased, it is actually what we call an unbiased estimator of the population variance. So we actually have to do that, and there's some theory behind it to show that it's an unbiased estimator of the sigma squared. So that's the reason behind it. I just wanted to tell you that really quick. We're not going to go into any proof to show that this one is an unbiased estimator of that. That's beyond the scope of the course, but if that's something you're interested in, you can certainly take another course in statistics that does some more mathematical statistics and some probability theory, and you'll be able to see that proof in there. Okay, what about degrees of freedom? So we're going to be heading into talking about more probability distributions. You've already talked about some. You'll have some more coming up as we get into the inferential part of the course. And so we mentioned something called degrees of freedom in that section when we talk about the t-distribution, specifically in other distributions. So the sample variance is calculated with n minus 1. This quantity is what we call degrees of freedom. So what's the origin of that term? There are n deviations from x bar in your sample. xi minus x bar is your deviation, and there's n of them. The sum of those deviations, as we already saw, was 0. And so n minus 1 of them are freely determined. But that last one is constrained by the fact that it's going to have to end up summing to 0. And so that's why we say that there's n minus 1 degrees of freedom. All right, so one more measure of spread. And as I said, we're not really finished with an exhaustive list with measures of spread. Your range is a very simple, easy way to find a measure of spread. And that's just your largest observation minus your smallest observation. And it's as simple as that. Now, I will go ahead and say this right now, that your mean that you have here, your sample mean, your sample standard deviation, and your range, they're all very susceptible to outliers. And the reason for that is because we incorporate all of our data in there. And so if there happens to be one unusual data point, it will pull around your mean, thus pull around your standard deviation, and of course pull around your range. So if you're concerned about outliers, you know you have some. Using the mean, standard deviation, range are not good. And I'll just go ahead and say that. If outliers, it's actually better to use the median and what we call the interquartile range, which you're going to see in a subsequent lecture. If your data is fairly symmetric, then go ahead and use your mean and your standard deviation. They're great. Okay, so what we've done now is we've gone through a couple measures of center, a couple measures of spread, and some numerical summaries, and this is the conclusion of the lecture.